Hey y'all, good afternoon. My name is Ellis McLarty. I'm in my last year of grad school at Clemson University, go Tigers. And I also work at Savannah River National Laboratory. I've had the pleasure of being there and working as a statistician with a team of geochemists. And today I'm going to discuss the work that I've done on that team and talk about how we can apply some pretty basic Bayesian techniques to a really cool and emerging field. So I want to start by providing you some background because maybe like me, your background's in math and stat and geochemistry feels way out of your wheelhouse. So this is TIMS. This is the actual instrument that we're using at Savannah River. And we like to call him Timmy when he's having a bad day. But TIM stands for Thermal Ionization Mass Spectrometer, and it's considered a gold standard in isotope measurements, especially when we're looking at ratios. Well, what does this mean when it comes to defense research and nonproliferation? Well, we can measure the ratio of different isotopes from elements like plutonium, and plutonium is an element of particular interest in nonproliferation research. So in 2024, early in that year, we installed a new TIMS thermoscientific Triton Plus TIMS. So one of the things that's important to mention here is that with a lot of work in DOE, we have a measure of security that we have to maintain. So we are looking at simulated data for TIMS in order to compare a frequentist and Bayesian approach. Why can't we use that real data? Well, we want to protect our customers' information as well as the samples that we're using in research. But on a practical level, it allows us to use a larger sample size so we can get a better result because we have more data. And we were able to classify this data such that it follows Poisson counting statistics or Poisson stochastic process. And so it actually is just a Gaussian distribution. So here's a nice little scatter plot of our simulated plutonium-242, 239 TIMS data. And again, this is just a particular isotope that ratio that is of interest for the nonproliferation community. This is just 1,000 simulated points. So let's talk about what practitioners typically use when they're looking at TIMS data processing. So these instruments come with a pre-installed software that often allows you to compute simple summary statistics, think your standard mean, mode, variance, all of those good things. And while these are important in practice, they're easy to compute and really simple to interpret, but with the power of statistical computing and programming languages at our fingertips like R, why don't we strive for something better? This is where Bayesian inference comes into play. And we've seen a lot of scientific fields apply a Bayesian process, but geochemistry is really lacking with this for some reason. And so my team and I at SRNL, we're interested in applying it specifically in a framework that is easily accessible to practitioners because we want people to be able to have these complementary methods. So why exactly is Bayesian inference important or practical in mass spec? Well, like we've mentioned, it's a data-driven approach, and it's sequentially updating when we have information available. This is helpful because for practitioners, the more runs they do on the instrument, the more they can learn about the data distribution itself. Furthermore, we have random treatment of parameters rather than fixed in a frequentist approach. Again, that constant updating allows us to perform better and to have a distribution to classify the data rather than just a singular point estimate. So here's just a nice little histogram of our Gaussian distribution. Nothing too out of the ordinary, but it's important to note that from this, we're getting our likelihood function for the Gaussian process, and we're going to get our normal density. And so at the poster session, I'd like to talk more about the priors, but for brevity's sake, we're going to skip over that. We're using a uniform prior in these images. But the important thing is that we're using an iterative approach. Specifically, we're doing a Markov chain Monte Carlo-based algorithm, a Metropolis Hastings. And what I want to point out about these images is that we have A, a lot of them, but B, we have some different shapes. And what we're showing here is that we can actually find different distributions in the posterior based on turret level. Turret means how many slots are used in the TIMS instrument. So we can perform a certain number of measurements, and we can vary that based off of the needs of the given day in the lab. So if you see an A and B, we have different turret levels shown, anywhere from 2 to 21 positions. And we're able to tune our MCMC algorithm such that it has sensitivity towards these turret positions. Some takeaways, again, we still think that a frequentist approach is a positive thing for practitioners to use, but why not introduce a more rigorous approach to uncertainty quantification to complement that? Priors allow for greater sensitivity and tuning, and we have that constant updating. What we're really excited about is our future work. This is actually, my research is a part of a larger project funded at Savannah River. It's going to be a part of a graphic user interface GUI that's using R-Shiny, and it's going to be free and open source to the public so that practitioners can toggle using a point and click method and insert their own TIMS data and easily have these data measurement and uncertainty quantification processes at their fingertips. I've also done some research on Gibbs samplers for uranium isotope data. That was really cool. So I'd be happy to talk about that more. And we want to continue expanding this to other elements to further support non-proliferation research and tune these so that they can be better for practitioners and make the field of geochem more accessible and stronger at large. Thank you. There's another slide. There's another slide with my information, but I'll be at the poster session if you need me.
Okay, cool. Thank you,
I don't know
Ellis.
where it went.
We have time for one question from the audience. Anyone? All right, then I have one. Oh.
Hello, thank you for the talk. Quick question for, I've been using Bayesian statistics for a while. Obviously you have to define your likelihood and then the priors. So the question is for people who are not familiar with Bayesian statistics, if the chains are not converging, how does someone in like, I guess a geology, like understand like it's not sampling correctly, it's not converging. I guess how do you impart that type of practical knowledge to them?
Yeah, thank you. What's your name?
Adam Watts.
Adam, thanks for that. So that's part of the process we're dealing with in creating this GUI is we want it to be accessible but still strong for practitioners. Part of that is by having the processes of the algorithm available for them to see. For instance, we'll have the acceptance criteria available within the MCMC, and they'll be able to see what that percentage is to see if it's performing as we need. But that is another consideration. One of the things I've been thinking about is having an option for users to toggle between different priors, say between a uniform and a Jeffreys for a small comparison. And this would allow for a side-by-side preview of how it's performing differently based off of their personal tuning requirements. But that is a huge consideration that we need to continue to work towards.
Perfect, thank you.
Of course.